Welcome. My name's Mike Howsden, and I'm the DevOps lead for the Atlantic. I've been using NGINX in some capacity or another for the last 8 years or so. My colleague, Frankie Dintino, and I put together this release automation system a while back, and we've been extending it a bit since then. The solution we came up with is interesting enough that I thought it worthwhile to share here. What makes this system different is we use only one virtual machine to provide nearly unlimited QA environments. All of our QA environments just run on one server or each application has one corresponding server that runs all of our QA environments. We also realized that there wasn't a lot of concrete examples of release automation and continuous delivery around, and we're just hoping to put some flesh on that sort of thing for people. People like to talk about that a lot right now. It's really popular, but a lot of times they talk about it in the abstract, and hopefully this will be a lot, have a lot more of the details and give people stuff that they could use to do it on themselves. To get started, I'll need to provide a bit of backstory. So let me talk about our development workflow. Developers work in 2-week sprints. New code is committed to a branch in Git. When coding is complete, a pull request is opened in GitHub for review. The pull request branch is then staged onto a beta server for QA. The pull request is merged into a branch named develop when code review and QA is complete. And the develop branch is merged into the master branch when it's time for a deployment. The old way we'd stage code for QA was a manual process. Choose between 10 pre-configured environments, SSH into a beta server that already has code on it, update that environment, update an out-of-date database, restart the uWSGI process, and hope everything turns out okay. Why was this bad? It was tedious. It was error-prone, and it was stateful. Developers would often get into a situation where they needed to completely wipe out the environment and recreate from scratch. And if someone had left uncommitted code, they'd be staging something grossly out of date. It was also very inefficient. There were enough instances to waste resources, but not enough to ensure one was always reliably available. Worst of all, NGINX played only a minor role. So we can do better. What's the business need? The business need is developers need to easily stage their work for peer and stakeholder review. So here's the beta's architecture overview. A developer submits a pull request or creates a beta branch, and that in turn kicks off a Jenkins build. The Jenkins file executes different scripts depending on whether that beta is a regular pull request or a long-running feature branch. We'll get more into the details of all this later. These are the components of this system. We use Jenkins for build automation, ref links to keep disk usage to a minimum, Supervisor D for managing uWSGI Emperor mode, Mod Passenger for our Noda applications, NGINX and uWSGI socket files for our Django application, nightly database snapshots to make sure our QA environments are using an up-to-date database, and we plug our long-running feature betas into an external proxy. I sort of touched upon it earlier, but we have 2 common use cases with different requirements. 1, simple bug fixes and minor features. 2, long-running feature branches. The typical process is a developer opens a pull request. The Jenkins build is automatically kicked off via webhook, and in around 10 minutes, a new QA environment is available, named off that pull request number. Product managers and QA or other developers can just browse to this URL and see the newly staged code changes and let you know like if everything's working okay. Here we can watch the Jenkins build process. Pip is used to pull down the latest Python dependencies, and npm does the same for JavaScript. We then run our various tests, and if they all pass, we continue on to the stage beta phase. If the tests fail, the pull request can't be merged until the failure is resolved. The magic that happens here is in that stage beta phase. That's where we find the logic that creates the QA environments. If you're familiar with Jenkins, you may recognize the blue ocean view. It's a much nicer way to visualize the Jenkins build process. The secondary flow is for long-running feature branches, database changes, and sometimes external review. It creates a distinct persistent copy of the database and registers itself in an external proxy with authentication. There's also a blacklist for named betas that we don't want externally accessible. A developer creates a branch prefaced with beta /. The Jenkins build runs, and in about 10 minutes, a QA environment with the beta's name is available. So what's the business value here? Efficiency. It cuts down on developer time spent on tasks unrelated to business goals. It automates repetitive and monotonous work. It improves coverage and consistency. There are no barriers to manual testing, even for trivial changes. Each build environment is created with the exact same process. Now I'm going to turn things over to my colleague, Frankie Dintino, to talk about some of the implementation specifics.
My name's Frankie Dintino. I was on the earlier slide. Been working with NGINX probably as long as Mike. Also maintainer of the NGINX upload module, but I work on more of the full stack stuff as well at the Atlantic. So I'm going to kind of go through the components that were touched on earlier one by one and dive into the details, starting with the Jenkins build. So what exactly is behind the steps you see displayed here on the Jenkins build screen? It's powered by a file committed to the root of your code repository named Jenkins file. It uses a declarative syntax to define steps, conditionals, parallel stages, and pass-fail states. It can then be hooked up with GitHub notifications so that builds are triggered by, for instance, opening a pull request or creating a branch and pushing it out. So here's a sort of slimmed down version of our Jenkins file with just the stage beta stage highlighted. So it starts off with a conditional. It checks the branch, whether it's a pull request, a branch that begins with beta /, or the develop branch, which we also want to QA before it gets merged into master. If those conditions are met, then executes the steps. So the first step is to run a script over SSH that creates the beta database. There's logic in this script so that databases are only created for named betas, i.e. the ones that begin with beta /, and then only if the database doesn't exist yet. Next, it creates a reflink copy of a base workspace. This is a technique to save disk space, and I'll touch more on that in a moment. So continuing on, the current build is rsynced over top of the reflink copy, and then uWSGI files are created, again using a script over SSH. This dynamically spawns processes in uWSGI Emperor mode. I'll explain that mechanism in a few slides. So returning to reflinks. The disk space savings using reflinks are quite substantial. A full build of the application, including static files and other resources, comes to about 1.2 gigs. But a typical diff of a build, which would only include a handful of Python or JavaScript files, as well as PyC files, only comes to about 3 megabytes. On Debian or Ubuntu, a partition would need to be formatted as BTRFS to enable reflinks. We use CentOS, and on Red Hat flavored Linuxes, you can create an XFS partition with reflinks. Currently, using XFS with reflinks also requires installing a custom-built kernel with a reflink flag enabled. There's discussion of making reflinks enabled by default in Fedora 29. Now I'll turn to our Python application setup. So we run uWSGI Emperor mode through supervisor D. A simplified version of the config is shown here. The uWSGI developers get a little cute with their terminology for subsystems in the server. Emperor mode refers to a way of calling uWSGI that dynamically spawns processes based on monitoring some resource. The simplest of these is a glob pattern, which is how we use Emperor mode. The star in this glob pattern is set up to match all of our build workspaces. Another name of a subsystem in uWSGI is Zerg mode. In Zerg mode, you have one very slimmed down uWSGI process that listens for requests and has a request queue. And you also have application workers, which when they come online, advertise themselves to the Zerg server, after which the Zerg master starts dispatching requests. So this is what the uWSGI config for the Zerg server looks like. This is the process that is very slim and just listens for requests and has workers attached to it. We use a few of uWSGI's magic variables, such as parts of the path and the ini file name, to determine what the name of the build and which application we're running inside of that build. So here, the build would be PR1234, and the application would be the Atlantic. We have a multi-tenant application that runs a CMS, the front end, and a few other aspects of the Atlantic system. We also use those variables to define the UNIX socket file that listens for requests and that listens for connections from Zerg workers. And so there at the very bottom, you see the Zerg server definition, which is a UNIX socket file that is then used in the Zerg worker to connect the two. We then use the cheaper subsystem, which is a way of only spawning uWSGI worker processes on demand and being able to scale up and down depending on the number of requests. Importantly here, we have an idle timeout of 24 hours. So if a pull request or a beta branch isn't accessed within 24 hours, it spins down all of the processes, and they won't spin up again unless somebody requests that server. So we can have pull requests and beta branches there more or less indefinitely, and if they're not being QA'd, they don't use up any more resources on the machine. And to tie it all together, we use NGINX to proxy to these uWSGI socket files. The magic here happens with the regular expression in the server name. Mike was the one who discovered that you could include a capture group in the server name regex, and then use it as a variable inside your server config. So we define the server root directory off of it, and then point the Zerg server's HTTP socket file in the proxy pass. You'll notice we're using proxy pass and not uWSGI pass. Which one you would rather use depends on your use case. If you're using WebSockets, you'll probably want to use uWSGI pass because it supports other protocols than just standard HTTP. But in our case, it was more important for us to be able to use standard monitoring tools and be able to access via HTTP the resources directly, and proxy pass gives us that ability. The configuration for mod passenger is similar in that we also use a regular expression for the server name. We run the AMP version of the Atlantic's website via an Express.js Node app. And so likewise, we pull the subdomain variable out of the server name and use it to point to the directory of the build and where the app lives and its startup file. And now open it up for any questions.
So all of your Selenium tests combined run in less than 2 minutes?
We don't have a whole lot. But actually the parallelism makes the test, you wouldn't expect that it would speed tests up that much, but it really does because a lot of it's I/O bound. So we run the Selenium tests alongside the non-Selenium unit tests and the node tests. And that process is actually about 5 minutes. We work pretty hard on trying to get these builds to be as fast as possible, just to like reduce frustration and to make the workflow as fast as possible for developers.
But when developers are doing a feature branch, do they have the ability to specify what testing that's run?
No, it runs all the tests.
All the tests.
Yep.
How do you notify the developer of kind of a link that's generated? I know it's a predictable pattern, but generally that doesn't work great when you have distributed teams. So how do you handle that part?
Basically, they just send, they send the link around more often than not. So like the pull request has, yeah.
Yeah, we've talked about having like a Slack integration or having it post a comment in the pull request, but we haven't really gotten around to it. Our team is still, we have maybe, 12, 14 people on our team, but they're all centrally located, so it isn't so much of an issue now. As we start to have more people who work out of the office, I think we'll want to have more automation in that department.
Yeah, and we actually brought that up like last week or something, and I think somebody said that they thought it was better to force the developers to communicate with the QA and product managers instead of automating that piece, because we wanted the relationship to get better. Is there? I'm just wondering, are there a lot of people that use uWSGI here? No. What about or Passenger? Anybody using Passenger? Everybody moved to NGINX unit? Okay.
Still use Passenger? Sorry.
No,
Yeah, the Node implementation of Passenger, I'd only used it in Ruby applications. The Node implementation, though, is actually pretty nice. Behind the scenes, it works a lot like our uWSGI setup, where there's like a Unix socket file that it creates in a temp directory, and then the process communicates. The Express server listens on that Unix socket file, and the location block that has the passenger directives communicates with that process that gets spawned. And in the case of Express, it actually patches some of the socket libraries in Node so that it redirects the listen request to this socket file. So it kind of does the things that we had in our like uWSGI Emperor mode setup, but it does so behind the scenes and sort of automatically. So we were pleasantly surprised with how easy it was to set up.
Yeah, it's surprisingly mature. It's like you get the advantages of something that's more mature because it's been widely in use with Ruby, and then Node's using it now. So I think that's what makes it so nice to use out of the box.
Yeah, otherwise we'd have to set up like our Express servers to spawn multiple processes, probably map them to port numbers that follow some sort of convention, and then create distinct NGINX configurations for the server definitions that point to those ports. And instead we can sort of do the simpler regular expression and point to like a understood socket file based on the, passenger application based on the build directory.
For like the CMS that you get back to users that the kind of log into in their work, or?
Yeah, so there's another property as part of the Atlantic, citylab.com, and that runs off the same code base. And then we have our CMS. We also actually have a few more Django applications and one extra Node application than the ones mentioned in these slides that all use a very similar build process. And the part of our configuration that relates to the multi-tenancy is that very last line there where we set the Django settings module. So we have a single repository for the different parts of the Atlantics app and which URL patterns are defined and which server it's associated with is defined by the settings file.
So given that you have one single repo for the entire application,
I mean, it actually depends to an extent right now. So there's like a node, the node service like basically uses the application as an API, but but there's still views like running from Django. So there is some front end stuff still running from Django, but we're kind of like on a migration path.
And only the named betas have their own copy of the database. Everything else uses a shared nightly clone of the database.
Is it possible to get a copy of these slides?
Yeah, so we don't have it uploaded just yet, but this GitHub repo, we're going to put the slides on there, as well as some example code that you can run through Docker to sort of show how you would spawn these environments and have basically a working copy of the code. If you want to like star that repo or whatever, I think we'll be able to have those up in a couple days. Sorry, could you say that again?
Performance tests. I mean,
no, not really. I mean, I think it would be a useful improvement. We use standard monitoring tools like New Relic, and we have like a Nagios system for more back-end monitoring.
yeah, so you can have some sort of profile of the application from New Relic right now, but beyond that, in general, I'd run performance tests as part of the, or like at the end stage or something like that. Any of these can be run through that. So basically, if we think that something's going to impact performance, then we just send the beta URL and then we run the test against it and pin it to, whatever, knowing that that system, just knowing that that system has a shared model, so it's not going to be quite as good. So, yeah, so, but the beta server in general is like way more beefy than our normal application servers. We also have other staging environments. We're not really talking about them, but the beta environments are, kind of like our 90% solution. They're so good that they solve like pretty much all the use cases. But if we needed like a separate server, we just spin that up as necessary. Or like sometimes we just pin a beta to a different database for, like we've been testing out a new version of MySQL. And so we do performance tests on that.
Your dependencies typically are running as sidecars, or are you like part of some kind of call service or anything your application is?
There's no real sidecar right now, though we're like working on it. Everything's kind of separate. There's just that API. It's more like it's like a service-oriented architecture. We're just beginning to build like a service-oriented architecture. That's just where we're at.
The AMP node application runs that way. So it queries the production REST API, and that's what powers the results that you see when you access the AMP version of the site.
Are you actually creating it looks like you're creating a completely separate database per one of these, and that I assume is usually based off whatever kind of wins out of the last replica that is made. Does that not start posing a disk space issue when you're doing production data? And how do you handle if it's a long-running feature of that database basically getting updated over the course of the months?
Sure. So we don't actually create a database for every one of these builds. Only for the long-running feature branches where the developer goes through the workflow of creating a branch that's called beta/. They can also open that as a pull request, but it'll only build the named beta version of it. And in that case, it will create another copy of the database with like a suffix based on that beta name and point to that. Whereas for pull requests that are just like bug fixes or minor features, where there is an expectation that the data will need to change, those just point to a copy of last night's nightly backup, and those are shared between all of the different PR builds. So like we only have a handful of these named betas at any given time, and we have a cleanup script that runs on a cron that deletes the databases after the branches have been deleted or the pull request closed.
And there's a refresh database script as well. So, so that's how that gets updated. Another alternative way that they can do, that a developer can do is they can just SSH into the beta server and update the database that they're pointing to the nightly snapshot. Then they get the constantly updating database. So it just kind of depends on their need, but we kind of leave it up to them. We haven't dictated all that workflow.
One thing I forgot to mention is that we talked about ref links, and that's important when you have developers who could maybe SSH into the server and edit a local settings file or something like that in order to customize it. Like maybe there's a secret key that they need to add to the environment to test their named beta. They SSH in and they might edit one of those unversioned files in the repo. And so ref links are necessary because it's copy on write. So they can edit the file and it won't modify the basis repository that it was created from. But in a production setup where it's assumed that the files are immutable, you could use hard links. And so instead of cp-ar-reflink, you would use just cp-al to create that basis, and then rsync-delete over top of that.
Yeah, I mean, we didn't really set out to optimize for like resource consumption like in this way. It just turned out that we could really easily, and then just have this one server that's kind of beefy that just handles all this stuff. And so it ended up being a nice design pattern. Yeah. We're good. All right, anybody else?
Thank you.
Thank you.